Take a look. Okay. Whoops, I need to take it off. Freeze. Okay, would you write the word angles there? So here's our objective. Here's our ICANN for today. I can use properties of central and inscribed angles, which we talked a little bit about yesterday. So we're going to use what we learned yesterday. We're going to talk about it in a slightly different fashion. So it says, find all the angles you can given the information. So I'm going to come over here. I'm going to make this just a tad bigger, and I'm going to shrink this down. So let's see. Let's think out loud here. Hey, if that's 130, that's got to be 50. Because that's a straight line. Linear pair, supplementary. Somebody tell me something else. Zach.
Because that one's 50, then the one across would also be 50.
This one down here or the one up here?
The one up.
The one up here? That one right there has to be 50?
Wait, no, it'll be the one at the bottom.
The one at the bottom. Can you tell me why?
Because the two sides are equal. So
yep.
Those two words, the base.
The two sides are equal. So on a triangle, if two sides are equal, then the angles that created those would be equal. Sometimes we call this the base angle theorem for isosceles triangles. So that one's 50. Next. Dane?
Couldn't you like do the two over there? So it's like alternate interior.
We'll do the two over here?
Yeah.
Okay, I could because this is marked as parallel. So if this is 50, this has got to be 50, right? And if this is 50, that's got to be 50. You can do that for sure. Okay, and I love the fact that he cited a reason for it, so we just don't have to take his word for it. Keely?
Wouldn't the last vertex angle be 80, and then it would have to be like vertical angles working?
Yeah, tell me why you think this is 80 though.
Because 80 is 100.
Very good. The three angles in a triangle equal 180 degrees. So if I've used 100 degrees between the two of these, I've only got 80 left for that one right there. Does anybody remember the technical name for that theorem? Psi? Triangle sum theorem. And then if you were listening, Keely even said this one has to be 80 because they're vertical angles. Okay. Anything else? Lizzie?
Well, you could measure the outside.
This one right here?
Yeah.
That external one, and it would be 130. And how do you know that?
Because 180 minus 50 is 130.
Yeah, because this makes a linear pair. Just the reasoning that we did down at the bottom. Okay, it's kind of like if we extended this one here, that would also be 130. It's vertical with 130. It's also a linear pair with that one there. Is there anything else that we can name in here? Yeah, Samara?
You could do like the other ones by the 80s. Those are.
Oh, very good. Nice. That's excellent. So this is 100 here and 100 here. Okay, very good. Anything else? Jack?
You could say the when things are congruent, like these two.
Oh, these. Okay, so this is great. Okay, so let me make sure I'm understanding what Jack is saying. Jack is saying that you could mark the two of these as congruent, the two sides as congruent. Is that correct?
No.
It's not
I
correct.
just realized that.
Okay, when you say congruent, would they be congruent to these?
No.
No.
But they would be congruent to each other.
They would be congruent to each other. So very good. We can mark that. Okay. Jack, can you tell us why we can mark that?
Because it's the one triangle. They're not the.
The one, yeah. Everybody got the one triangle thing?
Yeah.
You know what he's talking about? Can somebody give him the right words? Crew?
You can mark like the 80s as.
Hang on. We're talking about these sides right here. How can we mark those as congruent? How do we know they're congruent?
Because the angle 50 and that angle 50.
Okay, so the way I learned this is congruent angles cut congruent sides. So these are congruent angles. They will create congruent sides across from them. The opposite is also true. The converse of that is also true. So if you have congruent sides, you also have congruent angles. But are these the same length?
They could be.
They could be. They might look like it, but we don't know for sure, which leads us to the question at the very end of the warm-up. It says, whoops. It says, can you find side lengths? Why or why not?
You can for.
Can you find actual lengths of sides? The answer to that is no.
Well,
No,
can
you
for
can't.
Yes.
Why not?
sure there's a ruler.
Because there's nothing really to go off of.
There's nothing to go off of, and here's how I'm gonna put that. Okay, they didn't give us any lengths, no lengths to set up proportions or ratios.
Is that yellow thing on the wall?
Could you not find the 50-50 angle?
Yeah.
next to
Okay,
the 130?
so I'm gonna entertain this for 2 seconds, and then I'm gonna have to get fresh with Dane. Okay, if he doesn't stop this. Okay. Yes, that's a ruler. Okay, and I could measure that, right?
Yeah.
Does it say it's a scale?
Would it still be the same distance? Because I just dilated it, right? So even if you measured it when it was small, it's not the same measurement when it's big. You get the point? Okay, thanks. All right, so let's take a look at this. Okay, just like we saw with triangles, there is a ton of cool information. We had one tiny piece of information. We had an angle. We did know that two sides were congruent, and we did know that there were some sides that or some lines that were parallel. But we figured out a ton of information. Kudos to Samara for figuring out that 100, because a lot of people just skip right past that 100. Okay? So when we take a look at something like this, if we know a lot of stuff about circles and the lines and the angles that interact with those, we can figure out a ton of information. So we're going to talk about central angles for a second. We're going to describe these a little bit differently than we did before. So here's a central angle. It has a vertex at the center of the circle. That's why we call it a central angle. And whose sides contain radii. So technically speaking, on this diagram right here, this is a radius, which is just a chord, and this is a radius, which is just a chord. If that happened to be a line that extended past the edge, it's still a central angle. Okay, it doesn't have to be just a radius, but it has to contain a radius. Okay, an inscribed angle is an angle whose vertex is on the circle. So the entire angle is on the inside, or at least enough of it that we can tell, oh, this is the angle. So the green one here is the central angle. The inscribed angle is right there. And again, these could extend past there. They normally don't. They're normally just chords. Okay? So now we're going to talk about something slightly different. An arc is a portion of the circle's circumference. And we normally get that arc by cutting it up by sides or lines or points or something like that. So we normally chop things off. And this is what we call an intercepted arc. So I've got a central angle in green. I've got an inscribed angle in red. And then in blue out here, that's called an intercepted arc. So an intercepted arc is formed by lines or segments that intersect or intercept the circle. Either way would be fine. So both the central angle and the inscribed angle, they're going to cut out a piece of the circle, part of the circumference. We call that an arc. Mason.
This is kind of a random question, but how would you find the length of an arc?
We're going to get to that. Don't worry. We're going to do that in the next unit. You'll find that pretty fascinating. Okay? So the measure of a central angle, and here's where we start getting some information that's like, oh, you mean I know this? I can find out a whole bunch of other things? Oh, I thought that was a tech deck for a second. Okay? The measure of a central angle is exactly the same as the intercepted arc. So we measure angles, generally speaking, in degrees. We also measure arcs in degrees. Okay? Not arc length, just the arc. Okay? And the measure of an inscribed angle is exactly 1/2 of the arc that it intercepts. Now, this should kind of make sense, and I want to show you why. So if this is, let's say this is a 100-degree angle, this would be a 100-degree arc. So the arc from B to C would be 100 degrees, exactly the same as the central angle. Kind of makes sense, because if we chop this up into a bunch of central angles, kind of like a pizza, the angles would have to add up to 360, and all of the arc measurements would have to add up to 360. Okay? Now, here's kind of a rough estimate, kind of an argument as to why this is going to be exactly half. So if that's 100, that's 100. And if this is 100, the inscribed angle is going to be exactly half of that, so it's going to end up being 50. Here's a rough reason why. It should stand to reason that because the angle here, the vertex, is about twice as far away from the intercepted arc, that we move it back, and it's going to shrink the size of the angle that's going to have to intersect that. Okay, so the inscribed angle is half the measure of the central angle because the vertex is twice as far from the intercepted arc. So right, twice. So I'm hoping it makes sense. If we've got an angle that's this big to intercept that arc, if we move it back that far, it's going to have to get smaller to intercept the same thing. And if it gets twice as far away, it stands to reason it would be half the size. Everybody good with that? Okay. That's the bulk of what we're talking about today. So here's the deal. Find the measure of the missing arc and or the angles. And note that MAB, so notice that AB doesn't have a line over it. It's got a literal arc over the top of it. So it means the measure of arc AB. So on this one right here, we know the central angle is 80. So that means the measure of the arc would be 80. And that means that this would be 40 degrees. If this is 100, kind of working backwards from the example that I just gave, if that's 100, this has got to be 100 for the central angle. And the inscribed angle would be exactly half of that, so that would be 50 degrees. Mason.
How do we know that the inscribed angle is like, what if it was on like a different point on the circle?
We're gonna look at one toward the bottom of the page, and I hope it answers that argument, okay? If it doesn't, let me know, okay? So if you think about it, each one of these inscribed angles and central angles actually creates more than one intercepted arc. It creates the one on the inside of the angle, so to speak, and it also creates one on the outside. So a small one and a big one, if you wanted to think of it that way, okay? So we've got this small one, AB, and then we've got this big one on the outside here. So if the arc measures less than 180 degrees, we call it a minor arc. And on a minor arc, we name it by 2 consecutive points. So for example, over here, this is minor arc AB, okay? If the arc measures more than 180 degrees, then it's called, big surprise here, it's called a major arc. And on a major arc, even if there isn't another point on there, we put it on there so we can use 3 consecutive points in order to name it. So this is minor arc AB, like this. And if you want the other one that goes from A to B this way, you have to say A, D, B, so everybody knows which direction you're going. So if on a diagram like this, you just said arc AB, yes, most of the time they're talking about the minor one. But if because clearly there's 2 of them here, if you wanted to talk about the small one, you say AB. If you wanted to talk about the big one, then you have to throw another point on there so everybody knows you're going around the big side of it, not the small side of it. Yeah.
Why didn't they just change like capitals, like lowercase, like with lowercase?
Because capitals are used to represent points by convention, and lowercase letters are used to represent lengths, generally speaking. Okay? It's a good idea, but we run into some issues. Okay? So I got a question for you. What if the arc is exactly 180 degrees? What do we call it? It's not a major arc and it's not a minor arc. Has a name. Mason, you got it?
I have no idea.
D?
Is it a straight arc?
Nope. A good idea though.
That's what I was gonna say.
Okay. It's called a semicircle.
I was about to say that.
Okay? If you do something semi-annually is half, every half year. Okay? All right. So we can use the fact that there's 360 degrees in a circle along with the other information that we figured out to take one diagram and then say, hey, I know a whole bunch of stuff about this. So let's take a look here. I know that the inscribed angle is 60. So I know that the intercepted arc must be double that. So I know this has to be 120. That means the central angle is 120. Okay, now, this is going to get to Mason's point in just a second. The minor arc over here is 120. What about the major arc that goes all the way around here? It would be whatever's left of 360, so that would be 240 degrees. Okay? All right, we good with that? Okay, so here's what we mean. The measure of angle C, 120. Okay, I think on yours it says name. I changed it to vocabulary on mine. So the vocabulary is this is a central angle. Arc AB, because it's only 2 letters, it's got to be the small one. So the measure of that is 120, and we would call that a minor arc. Arc ADB, ADB is the big one, so we know the measure of that is 240, and that's a major arc. And then the measure of angle D is 60 degrees, and the best name for that is inscribed angle. You doing okay? Okay, now before you turn over, okay. Mason asked a second ago, hey, I kind of buy your argument about the fact that this is going to be half the intercepted arc because it's an inscribed angle. Twice as far makes sense as if it's over here, but Mason, if I moved it over here, was that kind of your argument? Okay, if you think about it this way, and I can't do this on the screen, but I can do it up here. It's like this, right? Okay, if I slide this over here, like this, so if I put it over here, this side gets shorter, but doesn't that one get longer? So it kind of balances out if you want to do that argument. If you want to see a proof for why it works in any situation, basically, if you slide it over this way or slide it over that way, it's still got to be 60 degrees to intercept an arc of 120. Is that kind of what you were going after? Okay. So just kind of think about that. Okay, flip the page over. We talked about this a second ago. A semicircle is an arc who measures 180 degrees. It should be named by how many points?
2.
Probably, what do you think? Probably 3. So they know which side you're going for. All right? An inscribed angle that intercepts a semicircle. So an inscribed angle that intersects a semicircle. So here's a semicircle, 180 degrees right there. There's your semicircle. There's the inscribed angle. It should be half the arc. So what is it? A blank angle? My gosh, I gave you a gigantic hint. Lizzie? A right angle. Very good. It's going to be a right angle. If it's inscribed and it intersects an arc of 180 degrees, it's going to be half that, so it's going to be 90. And think carefully on this one. A central angle that intercepts a semicircle is a blank. So here is a central angle that intersects a semicircle. Looking for one word. Ooh, very good. Nice job. Diameter.
Great job.
It's a diameter. You could say that it's a straight angle or something like that. That would be okay.
What if you said it was 4?
Then we'd get in trouble. Okay. All right. Congruent arcs. Congruent arcs with the same measure or on the same circle or on congruent circle. So if they are congruent arcs, okay, they can be congruent on the same circle because it's the same size, or on another circle that's the same size, then they can be congruent. But here's the problem. If I say I've got a 120 degree arc on this circle that's this big, and then I make it this big, the actual arc would measure in degrees the same, but it would be longer in real life or shorter, okay? So we got to be using the same circle or congruent circles. So central angles that intersect the same arc or congruent arcs are congruent. Inscribed angles that intersect the same arc or congruent arcs are also congruent. So here's what it means. This is the same circle. If that's 80 and that's 80, this has got to be 80 and this has got to be 80.
Yes, that makes sense.
If this arc is 50 and I've got one over here that intercepts that 50 degree arc, that's got to be half, that's got to be 25. And this angle over here that's vertex is at D, it's also an inscribed angle, but it intercepts the exact same arc, so that's got to be half of that, that's got to be 25 also. Okay? So if they intercept the same arc or congruent arcs, okay, then they've got to be congruent. All right, everybody good there? Whole bunch of funky information. Take a look at this. Okay, you can add and subtract angles just on circles and arcs, just like you can with other regular angles. So let's take a look at this. It's got some important piece of information. FH and JK are diameters. So that's a diameter and that's a diameter. And it says find the measure of each arc or angle. Okay, so if that's a diameter, and this is 65, and this is 50, that makes 115 altogether. So that makes this 65. This one's 65 because it's vertical. And can somebody tell me what this one is? A couple ways to do it. Easiest way to do it would be this is a diameter, right? So there's 180 degrees on this side, and we use 65 of them, so that would make this 115 degrees. Am I correct about that?
Yes.
65 degrees for the arc, 115 for the arc, because these are all central angles, 65 degrees, 50 degrees. Okay, remember we started with, if you know some information about circles, you can have a couple pieces of information. You can fill in a whole bunch of stuff. So the angle FAJ, 65 degrees. LAH, and we're looking for an angle, LAH, also 65 degrees. Another angle, KAF.
I know it.
KAF. Hey, crew, what is it?
115.
115. Arc JL. Side. 50. Arc LH. Yep.
65.
65. Arc HK. What do you got, Jack?
65.
65. HF.
180.
HF.
Oh, yeah.
180.
Would it matter which way we went?
No.
Should they have specified?
Yes.
Probably, but it's going to be 180. Okay. JF. 65. JH. 115. And JHF. So they were specific here. JHF. What do you got?
Freaking science.
How'd you get that?
I can explain.
360 minus the 65, 295 degrees. Everybody good there?
Yes.
Okay, raise your hand if you're feeling pretty good about this. All right, let's slide down here. Got a couple more to take a look at. Okay, got some information. Those are diameters. Angle FHM is 40 degrees, so we got that marked. So that's this guy right here. I'm going to put a little dot in there. Arc HK is 60 degrees. Got that. Arc JL is 50 degrees. Got that. Now I got work to do. No perfect way to do this. Okay, if this is 50, everybody take a look. If this is 50, it's intercepted by that central angle right there. So this is going to be 25 degrees. If this is 40, that's an inscribed angle. So that means from here to here would have to be 80. We'll see if we can figure out some other stuff down the road. If this is 60 degrees, that's an arc length, then the central angle is 60 degrees. The one across from it is 60 degrees because it's vertical. And this one over here is 60 degrees. Anything else? Jack?
That one above it is 120.
Okay, this one right here is
Yeah.
120 because if this is 60 and that's a diameter, this has got to be 120, which is kind of cool because if this whole thing is 120 and that's 80, that means this is 40.
Yes. Yes.
Good there?
Yes. Wait.
Oh,
It's because JK is the diameter.
so now we know what LH is.
Okay, does anybody know what the measure of this angle is right here? What is it? 90 degrees. Because it intercepts a diameter. Now, is that enough that we can get started labeling some of these? We could figure out everything, but maybe we don't have to. JF, arc JF, 60 degrees. Got that. LH.
I know it.
Ooh, I don't have that yet.
That's what I was gonna say.
But we do know this is 50 and this is 60. What is it?
70.
This one's 70 because this is 180 from here to here, 50 here and 60 here. That's 110. 180 minus 110 is 70. So this one's 70 degrees. Perfect. Angle JKL. JKL. Got that one, 25. Arc FM. We got that one, 80. Angle HAK. HAK. Yep, 60. Arc KF. KF. 120. Yep, we figured that one out. Arc MK. 40. We got that piece right here. And arc JGK. JGK. 180 degrees down here, 180 degrees up here. So this would be 180 degrees altogether. Okay. Everybody good with that? Okay. Kind of cool that you can take a few little pieces of information and figure those out. We're going to take a look at the last couple, and then I think you're going to be happy with the assignment. So take a look here. It says find the measure of angle 1, 2, and 3 and arcs AC. So AC is this one. And ACD. ACD is that whole thing right there. So ACD would go all the way around there. You can dive in and do it however you want. Samara, you got an idea?
Well, I was just gonna say 125 is 55.
Okay. So this will be 125, and this one over here is 55. Very good. By the same argument, wouldn't this be 55 degrees?
Yeah.
And what would be left over here isn't this 125? Make that look right, 125.
Oh.
If this is 55 degrees and it's inscribed by this angle right here, it's intercepted by that inscribed angle there, 27 and a half, 27.5. So angle 2 is 27.5 degrees. Wait a second. Those are both radii. So this is an isosceles triangle, and lo and behold, half of 55 is still going to be 27.5. So that's going to be 27.5 degrees. Measure of angle 3. Oh, come on. 55. 55 degrees for a couple of different reasons. AC is going to be 55 degrees. And what about ACD? Did we need any of these extra pieces to figure out what ACD was? Why not? Zach?
Because it is
Yep, you're right.
diameter.
It's a diameter, and a diameter cuts it in half, so that means it would measure 180 degrees. Everybody good there? Okay. Take a look at this last one. Set it up.
Wait, what was
Dane, take a look at the last one. Set it up.
what was three?
Rats.
What's that?
What was three?
Angle 3? Because it's a central angle.
Difficult.
What do you know about both of them?
They're the same angle.
Lizzie says they're congruent. Somebody tell us why they're congruent. Mason?
So it's because they're both inscribed angles that go to the same point.
They intersect this same arc. So
Yeah.
that means if they intersect the same arc, then they've got to be congruent, which means we can say that angle 1, 2x minus 13 has to equal angle 2, x minus 3, and then we can solve from there. Okay? I'm going to move the x over, move the 13 over. So x is 10. Okay.